very popular but hard to understand deep learning models. And this is joint work with Google Big Picture team, or People Plus AI research group led by Fernanda and Martin. So we have seen many new visual analytics tools for deep learning today in this session and over the past couple of years at the VIS conference. But when we think about what type of users these tools target, almost all tools are designed for machine learning engineers or experts, as noted in the first session of this, first talk of this session. But we have a question: is there any other type of users who may benefit from visualization? One example is non-experts who want to learn deep learning models. As deep learning has received a lot of attention, many practitioners or students want to learn this new technology. And visualization has successfully been helping these people learn machine learning. Chris Ola's blog and Andrei Kaparty's demo shown here are great examples. I believe that our VIS community can contribute a lot more to this new area of teaching machine learning to non-experts. A couple of years ago, our colleagues at Google developed TensorFlow Playground, a new interactive educational tool for users to visualize neural net models and play with them. And it was a great success. It's now part of the every Intro to Machine Learning course at Google, and it has also been adopted by many top universities in the US and around the world. However, a key challenge in developing such educational tools is the complexity of modern deep learning models. These days, the models are becoming increasingly complex, consisting of many operations that interact with each other. One great example is Generative Adversarial Network, or GAN. As a generative model, the GAN can generate new synthetic data that look like real data. And these face images shown here are fake images produced by GANs, not from real people. While GANs have been one of the most popular topics in machine learning research since proposed in 2014, but they are very hard to understand and very difficult to train, even for experts. Why are GANs difficult to understand? One key reason is a GAN consists of not one, but two different neural networks that compete against each other. These two neural networks are called a generator and a discriminator. And let me briefly tell you how they work. The authors of the paper use an interesting analogy. We can view the generator as a counterfeiter who makes fake dollar bills, and the discriminator as a police who spots the fake bills. The key idea is that as the two players face off, they'll both get better and better. For example, when the counterfeiter first generates fake bills, they may not look good enough, so the police can easily spot them by differentiating them from real dollar bills. But the counterfeiter can revise their skills from how the police worked. And the police is also revising their skills. And this is not a common training process of deep learning models, so it is difficult for people to get a conceptual understanding of how they work. So we wanted to effectively describe this concept using interactive visualization. So we developed GANLab, the first interactive tool for learning generative adversarial networks. GANLab has a novel visualization design, which is great for people to understand the complex dynamics of GAN's training process. And with GANLab, users can interactively train models and play with them to actively learn about GANs. Also, our fully browser-based implementation approach significantly broadens people's access to our educational tool. And now let me tell you more details about how we designed this GAN. So back to this diagram. To effectively visualize the concept of GAN shown here, we made some important design decisions and developed some new VIS techniques. First of all, we had to decide which data sets to visualize. In this analogy, data sets correspond to dollar bills. GANs are often used to generate high-dimensional image data, but we decided that our GAN model generates two-dimensional data points. Here you can see that data points are distributed under this ring-like distribution. Why are we doing this? First of all, now we can easily visualize multiple data points at once and show how they are distributed. And here data points are distributed under a ring-like structure. It's very useful and effective in explaining GANs because data distribution is what generative models like GANs are trying to capture and learn during the training process. Also with this two-dimensional data point representation, it's much easier for learners to track how data points are transformed throughout the several components of the models. For example, now you can easily compare the real data points shown in green and the purple data points. So based on this two-dimensional data representation, we implemented the very first prototype of GAN map. Here, green dots represent real data, which a GAN model aims to learn. And purple dots are what the generator created. And users can start the training by clicking the play button on the top of the interface. So now purple data points are continually updated, and we expect that after several iterations, this purple dots will nicely overlap with green dots. So this visualization dynamically shows the result of models, but it does not show any details of any internals of GANs. So like how model created this purple data points. So we wanted to visualize how the generator produced these purple data points. And these purple data is the output of the generator. So to visualize the generator, we thought about this question, what about the input? So actually the input is also a two-dimensional, set of two-dimensional data points, but they are random data. And now what we can learn from this diagram is the generator is a function that simply transforms each input data point on the left into a new position on the right side. So that means if we can effectively visualize this transformation, that visualization will explain the behavior of the generator to some extent. So our approach to visualizing this transformation is to represent the distribution of data as grid, showing density. So on the left side, now we are showing this data point as a grid. So here are darker cells representing more samples in smaller space. Then we can map each cell in the grid into new positions based on the generator's transformation function. And we can repeat this process for all the grids, all the cells in the grid. Now then we will get a warped and twisted version of the grid on the right side called manifold. And now we can use this manifold as a visualization of the generator. And it also, and we can also show this generator's manifold as an animation of how the input space transforms from input random space into the twisted version of the output space. So here's another example. Suppose a GAN model aims to learn this mixture of two Gaussian distributions, one on the top left and the other on the right side. So if we only show purple data points, it's a little hard to see whether a model is capturing this distribution well. But when we plot manifold on top of here, now we can see what the model has been trying to have two dense regions by squeezing areas near those two means. Also, it's easier for users to compare these distribution of purple data points with the green data points. So that's for the generator. And now also we wanted to visualize the discriminator, the other component of the GAN. It was relatively simpler because discriminator is a binary classifier, so we decided to use the same technique used in TensorFlow Playground, as TensorFlow Playground is also for visualizing binary classifiers. So here the discriminator is visualized as two-dimensional heat map indicating the discriminator's classification whether a dollar bill, data point is real or fake. And if a data point is located under green regions, that means the discriminator will classify that point as real. And if a data point will be in purple regions, it will be classified as fake. So combining all the visualization I mentioned, data points, discriminators, heat map, manifold, we got this visualization. But also, on the left side of the interface, we displayed a list of hyperparameters for users to pick, such as the number of layers, number of neurons, or units. However, when we tested it with some pilot users, they commented that the interface is a little hard to use and interpret. It was mainly because users had to develop mental models for GANs in their heads to keep track of how things on their interface, like the number of neurons, map to different components in GANs. So this finding prompted us to add a new view called model overview graph on the left side of the interface, inspired from the architecture diagram for GANs. And this new design, this new multiple view design, is very helpful for improving the usability and utility of our system. First of all, it is great for users to build mental models for GANs now, because we have a visualization for generator and discriminator separately within the context of the model architecture. Also now, users can easily see data flow among the components using, as we show this architecture as a graph. And we can also introduce a nice feature like the slow motion mode here to show how each component of the model contributes to the training process during this iterative process. Lastly, now hyperparameters are positioned near the associated components. For example, the number of layers for the generator is located under the generator. So now users can easily locate these hyperparameters when they adjust these hyperparameters. Let me show you a quick demo of how people can train a model in GAN. First, users can draw a distribution for GAN to model. After that, users can set hyperparameters using drop-down menus and some buttons on the left side. Once they are done with setting all these hyperparameters, they can click the play button on the top to start the training process. Then purple data points show up on the right side, and they're continually updated. And they can also now visualize the discriminator by clicking the checkbox, and discriminator visualization for the discriminator is shown on the right side. And also, users can dynamically adjust hyperparameters to guide the training process based on this visualization. Also, we can visualize the generator here to see how purple data points are distributed and how generator made this distribution. And also, we can show the animation of how it transforms the input space. And users can keep changing the hyperparameters to learn about how these hyperparameters affect the training process, and we are showing like this distribution dynamically. And users can do this like playfully with using different data sets or different type of hyperparameters to actively learn about how GAN is working. In implementing our educational tool, there was one important challenge. We wanted to make our tool accessible to as many people as possible. However, conventional deep learning visualization systems require servers that use significant computing resources or expensive hardware like GPUs. But non-experts or students may not have access to such expensive resources. So to tackle this challenge, our idea is to put everything, including model training to visualization, into browsers by using TensorFlow.js, a new JavaScript-based library, deep learning library, developed by our colleagues at the Google Peer Group. So now people can access GANLab using only their web browsers without the need for installation or specialized backends that uses server-based deep learning library. And this approach significantly broadens people's educational access to tools like GAN. And I'm excited that we open sourced GAN last month and our release went viral. Many people over the world have shown interest and visited our websites. That is a live system and a distill-like explanatory article. And you can also try it now using your laptop or even using your smartphone. And to sum up, we developed GAN, the first interactive VIS tool for learning generative adversarial networks. And we believe this type of interactive educational tools developed by our VIS community can play critical roles in promoting people's understanding of deep learning and the new AI technology. And I hope this work will help inspire even more research on this topic. And finally, I'm graduating this year, and on the job market, so if you're in academia and have positions, then please let me know. I'll be happy to check. And that's all for my presentation. Thank you very much.